So how is the 32 and the 8 related here? I mean, what is the general rule? If I give you a number and I want to reduce that modulo 24, what do I do? Any idea? Yeah? The remainder, right, the remainder. So what you do is, you take this number, you divide it, teilen, right? And you're not really interested, normally if you divide, we're interested, how often does this number fit in here? You know, in this case, the 24 fits in 1. The only thing you're interested in is the remainder, the rest, right? And it turns out the remainder, the rest, is 8, okay? So this modulo operator is also remainder operator, or rest operator, whatever you want to call that. And what I'm going to tell you now, I give you a more formal definition of this modulo operator. So let the three integers a, r, and m, a, r und m, be element of Z, natürliche ganze Zahlen, and m is positive. And then we write A is, so this is not called equal, this is not called gleich, this is called equivalent. It's equivalent to or congruent R modulo m. And now comes actually the important thing. If m divides a minus r, i.e. das heißt, i.e. ist das heißt in Latin, and just a mathematical symbol for divides, if m divides a minus r. So this is just a new math notation. This bar, this strich here, okay, reads m divides a minus r. Okay. What is this? So now what this boils down to, we have to look at these three numbers which actually have names. I should introduce the names at this point. This a actually doesn't, this is kind of the number we normally deal with. We want to reduce typically. This m is surprise, called the modulus, and r is called the remainder, der Rest und Modulus. So they're very rather similar names in German. Let's say a is equal to 13, m is equal to 9, and what you would like to know is what is r. One trick you can do is, forget about this whole definition here, you do what we said before. You take 13 and you divide, okay? So how often does the modulus fit into the 13 here? Wie oft passt das rein? One time, very good, very good. What is the rest? What is the remainder then? Very good. Okay. This is one way of doing it. And now let's check whether this is what we kind of did almost by intuition, because most of us have heard about modular reduction, whether this is in accordance with this definition. So we look at this difference. We look at a minus r. What is a is 13. The r we just freshly computed is 4. This is 9. And now what we have to check is this a minus r, is this divisible by 9? And of course, 9 is divisible by 9, so that works out, right? So that works. The first thing we want to investigate is, maybe call that 1a, is how do we compute the remainder? So computation of the remainder. So that means given is very often, in fact, a and m in z als ganze Zahl. And now the question, how do we compute r systematically? So what we do is you write a, kind of you start this way. You write it this way, where a equals to blank, right? 3 Kästchen, right? Freilassen, 3 little square space. This is how you start. And now you do exactly what we did verbally before. You look how often does the m fit in into the a, and there's a fancy term is q for quotient, which we're not going to use much in this lecture. We're going to use it at some point again. Quotient. So it's in the beginning, you can ignore that. And we talk about Euclidean algorithm in a few weeks, in a few months, 3 months or so, we're going to use it. But the thing we are really interested in is r. Let's look at a is 42. It's maybe a little larger, and we look at a modulus equal to 9. So what we do now, if you want to have the remainder, we write that exactly in this form, and we ask ourselves, how often does the 9 fit into the 42 in order to get the quotient out? And what is the result? How often does the 9 fit in there? 4 mal, genau, 4 times. And what is the remainder? What's the rest here? 6, right?